Today we're going to prove the power rule for derivatives, and even though this is kind of an easy formula, this is one of the first things we learn in calculus, it is not that easy to prove it. Well, I mean, it's easy, but it's a bit tricky because you have to take the limit from the limit definition of derivatives as h goes to 0 of x plus h to the n minus x to the n all divided by h. And what's the problem with this is that we have x plus h to the n, and to expand this out we need the binomial theorem. It's a bit tricky and we're not going to do it this way. But what if I told you that there's an easier way to prove it? And this way is by induction. So we're going to prove this statement here in 2 steps. The first step is to prove it for some index, for example n equals 1, and you might ask why n equals 1, because it's easy and we'll see later on why it's useful. So let's do it. What is the derivative of x to the first power, because n equals 1? Well, this is the derivative of x. Now we can use the limit definition of derivatives, so this equals to the limit as h goes to 0 of x plus h minus x all divided by h. Obviously we can cancel out x and minus x, and we can just simplify h and h, so this gives us 1. And this is easy, and let's see whether this works. So the right hand side is 1, and let's see whether 1 times x to the 1 minus 1 is indeed 1. Well, 1 times x to the 1 over minus 1 is x to the 1 minus 1. 1 minus 1 is 0. X to the 0 equals 1. We got 1 and 1, so this is indeed correct for x equals 1. Sorry, for n equals 1. Now, what's the second step? Well, how do we know that this formula works no matter what n we substitute in? So this has to work for every natural number n. It works for n equals 1, but we don't know whether it works for n equals 2, n equals 3, n equals 1000. So what can we do? Well, we have to make an assumption. Our assumption is that this formula works for some index n, and this is what we are trying to prove. So assuming that this works for some index n, then this is going to be true for the next number, so x to the n plus 1. So if we replace everything by n plus 1, we get n plus 1 instead of n, times we have x to the n minus 1, but we have n plus 1 minus 1, and we get n. Then this is going to be true for every natural number n. But why is this the case? Well, if assuming that this is true, we can prove that the next number n is going to satisfy this formula here, and we prove it for some index, for example n equals 1, then this is going to be a kind of chain reaction, because this is true for 1, but if it is true for 1, it is going to be true for 1 plus 1. So it is true for 2, then it is going to be true for 2 plus 1, that is 3, and so on. So this is a kind of chain reaction to prove everything. Alright, so we've proven the first step. Now we have to go through the second step. Alright, this is easy. I promise this is easy, because the derivative of x to the n plus 1, we can rewrite this as the derivative of x to the n times x to the first power, so x. But now here we can apply the product rule for derivatives, and we know how to do it. This is the derivative of the first one, so x to the n times the second one plus the derivative of the second one, so x, times the first one, so x to the n. But now we know what the derivative of x is, because we found it earlier that this is 1. So all this stuff here, this is equal to 1. Whereas here is where we need to use our assumption, because the derivative of x to the n, because our assumption says that this is n times x to the n minus 1. This is a kind of guess to what the derivative is. So we can write this as nx to the n minus 1 times x plus x to the n. Now we have this x multiplying this, so x to the n minus 1 times x is x to the n minus 1 plus 1, so it is x to the n. So we have n times x to the n plus x to the n, and as you can see, we can factor out x to the n and we get x to the n that multiplies n plus 1. As you can see, this one is the same as this one, so well, we managed to prove our power rule, and in my opinion this is the easiest method to do it compared to the binomial expansion that is a bit trickier than this. So if you enjoyed this video, leave a thumbs up, subscribe to my channel and share this video with your friends. As always, until next time, bye.